States of matter and intermolecular forces. In this chapter, we will discuss the nature of intermolecular forces and how they determine the states of matter, as well as properties of different states of matter. We will focus primarily on liquids. The behavior of molecules in the three common states of matter is determined by the nature of intermolecular forces acting between atoms and molecules. In Chem 1, we studied two types of bonding. First, we have covalent bonding, which results from the sharing of electrons between atoms. Secondly, we have ionic bonding, which arises when electrons are given up by one atom and accepted by a second atom, resulting in permanently charged ions, which are attracted electrostatically. Intermolecular forces, which are also known as non-covalent interactions, do not involve the sharing or transfer of electrons. We will discuss the origin of intermolecular forces in a few minutes, and spend the entire next lecture discussing their features. To begin with, we will cover some very basic ideas. As atoms or molecules approach one another, they begin to feel a weak attractive force that is not as strong as chemical bonding forces. Once the atoms or molecules approach too closely, their nuclear charges begin to repel, causing a rapid increase in energy. This is demonstrated by the graph on this slide, which shows the potential energy as two molecules or atoms are brought close together. At very far separation, on the very right-hand side of the graph, we see that the potential energy, or the red line, is effectively zero, meaning that the two molecules or atoms do not feel each other. As we move in toward the origin, we see that the red line dips below zero, indicating that we are seeing attractive forces as the two atoms or molecules approach. Once we hit the bottom of the well, the energy begins to increase rapidly as the nuclear charges begin to feel one another and the repulsive forces begin to push the molecules apart. The state of matter that is observed depends on two competing quantities. First is the depth of the energy well. How deep that well happens to be indicates how strong the forces are. Secondly, the kinetic energy of the molecule. Recall that kinetic energy is the energy of movement. The more a particle moves, the greater kinetic energy it possesses. At the molecular level, kinetic energy is closely related to the temperature of the system. The higher the temperature, molecules will tend to have a greater kinetic energy. They will move around with more energetic motions. The lower the temperature, molecules tend to have less kinetic energy. When the kinetic energy is large and the well depth is small, the intermolecular forces are not very noticeable. This is analogous to when you are traveling rapidly in your car and you happen to hit a small speed bump. The faster you're going, the less noticeable the speed bump tends to be. When kinetic energy is small and the well depth is larger, the intermolecular forces become quite noticeable. Again, if you're traveling at a slower speed in your car and hit a speed bump, you're going to be jostled around to a greater extent. The comparison between the kinetic energy of the particles and the well depth of the attractive forces will determine the phase of matter that we observe. The gas phase is defined to be when the kinetic energy of the molecules is much greater than the magnitude of the intermolecular forces, or the well depth. Particles move with sufficient energy that the molecules are negligibly attracted and move freely. This is demonstrated by this short video clip. The particle is moving with sufficient energy that as it approaches the second particle toward the origin, the well is negligible compared to the energy of the particle, and so the particle just ignores the well as if it doesn't exist. Once it hits the repulsive force due to the nuclear charge of the second atom, it is repelled and bounces back. The particle does not become stuck in the attractive well, and it will continue to bounce around from molecule to molecule. This gives rise to important properties of gases. First, a gas in a closed container will expand to completely fill the container. Since the particles are not attracted to one another, they will not be pulled toward one another and will expand to fill the container. Secondly, a gas will take the same shape and volume as the container. Again, this is due to the fact that the particles are not attracted to one another and will move around freely in the full shape of the container. Thirdly, a gas is largely compressible, which means that we can push on the gas and cause it to decrease in volume. Since the kinetic energy keeps the molecules far apart, this minimizes the repulsive forces, meaning that the gas particles do not want to tend to stick together. Fourth, a gas will tend to flow readily. The fact that the particles are not attracted to one another allows them to move freely in an expanded region of space. And lastly, a gas undergoes rapid diffusion. This means that the particles of gas can spread rapidly throughout the gas. Next, we will consider the solid phase, which is defined to be when the kinetic energy of the molecules is much smaller than the magnitude of the intermolecular forces, or the well depth. In this case, the particles move with so little energy that the attraction is very significant, and the particle actually gets trapped by the attractive forces, and therefore cannot move freely. Again, this is demonstrated by this short video clip. In this case, the particle moves with sufficiently low kinetic energy that as it approaches the attractive well, the effect of the well is very noticeable, and the particle actually becomes trapped and cannot escape the well once it has entered the well. This causes the particles to remain very close together in the solid phase. This strong attractive force gives rise to different properties of solids. First, a solid in a closed container will no longer expand to completely fill the container. The molecules are attracted to one another sufficiently strong that they will stay stuck together and not expand to fill the container. Secondly, a solid will maintain its own shape and its own volume. Again, this is due to the fact that the particles will be stuck together in a very ordered structure, causing it to keep its own shape and volume. Third, a solid is incompressible. The molecules are already trapped in the well, and any compression results in strong repulsive forces, which prevent the molecules from moving closer together. Fourth, a solid will not float. Being trapped in the well, the particles are not free to move from one region of space to another, and so they will stay stuck together. And lastly, a solid undergoes extremely slow diffusion. This means that particles spread extremely slowly within the solid, so that if we add an impurity molecule into the solid, it may move throughout the solid, but it will do so only at a very, very slow pace in a very short distance. The liquid phase lies between the solid and the gas phase, and is defined to be when the kinetic energy of the molecules is approximately equal to the magnitude of the intermolecular forces, or the well depth. In this case, the particles move with enough energy that the attraction is noticeable, but collisions with other particles can increase the energy enough for the particle to escape the well. Therefore, the molecule does move around, but less freely than in a gas. In this video, we see that the particle moves with a small enough kinetic energy that the well is noticeable, and the particle actually does become temporarily trapped within the well. However, at some point, a second molecule jostles it enough to where it can pop the first out of the well and make it free again. It will move from well to well, being attracted and then knocked loose throughout the remainder of its motion. The intermediate kinetic energy of liquids gives rise to its properties. First, a liquid in a closed container will not expand to completely fill the container. The attractive forces are sufficiently strong to prevent the liquid molecules from freely expanding. Second, a liquid will take the shape of the part of the container that it fills, but it will maintain its own volume. Due to the fact that the liquid cannot expand freely, it will maintain its own volume rather than take the volume of the container. But because it can flow, it will take the shape of that part of the container that it does fill. Third, a liquid is practically incompressible. This is due to the fact that molecules spend most of the time trapped in the well, and compression results in the strong repulsive forces. Anytime you use hydraulics, you are making use of this particular feature of liquids. Fourth, a liquid will flow readily. If a liquid is poured into a large container, it will not maintain its own shape, but will move about freely in order to take the shape of the container. And finally, a liquid undergoes slow diffusion, meaning that particles spread slowly in the liquid, but much faster than in solids. This is a familiar idea to us. If we ever put a drop of food coloring in some water, we will see the food coloring diffuse throughout the liquid, but it will do so at a fairly slow rate. The last topic that we will consider are phase changes, and we will discuss these in much more detail in a later video. But at this point, we need to be aware that there are two ways that we can affect a phase change in a material. First, we can change the temperature. By increasing the temperature, we increase the kinetic energy of the molecules, causing the attractive forces to become less noticeable, which results in a change to a less condensed phase. An example of this is when we heat ice. Eventually, the heat being added to the ice will cause all of the solid ice to transform to liquid water. Conversely, by decreasing the temperature, we lower the kinetic energy, which causes the attractive forces to become more noticeable, which results in a change to a more condensed phase. If you ever have an iced drink outside on a hot summer day, you will observe this particular process. The water vapor, which is a gas in the air around your cold drink, will be condensed into a liquid on the surface of the cold drink due to the decrease in temperature. Secondly, we can change the pressure. By increasing the pressure, we force the molecules closer together, causing the attractive forces to increase, which results in a change to a more condensed phase. This is commonly used in the process of liquefying gases, such as propane, which you use in your propane grill or in your propane heater. Conversely, by decreasing the pressure, we allow the molecules to move farther apart, which causes the attractive forces to decrease and results in a change to a less condensed phase.